In this video, I'll be solving some force problems, primarily focused around force components, weight, and normal forces. And in future videos, I will cover other forces such as spring forces, friction, gravitational forces, and others. So in this first problem, we have a crate sitting on a ramp that makes an angle of 30 degrees above the ground. The crate is being pulled by a force that is 40 newtons and makes an angle 20 degrees above the surface of the ramp. And we're asked to find the horizontal and vertical components of this force. So first, I'm going to draw a ramp, and this ramp makes an angle of 30 degrees with the ground. And we have our crate, and it is being pulled at an angle that is 20 degrees above the ramp surface. So this is our force. And so if I draw a XY coordinate system, this force is going to be at a total of 30 degrees plus 20 degrees above the x-axis. So if I wanted to get my horizontal and vertical components, I need to make a right triangle. So this is my force, and this is the x component, and this is the y component. In this triangle, the y component is my opposite side, the x component is my adjacent side, and as always, my vector is the hypotenuse. So I can use my definitions of cosine and sine. Cosine is adjacent over hypotenuse, or fx over f. This will give me the x component of the force is f cosine theta, or 40 newtons, times cosine of 50 degrees. If you plug this in, you should get 25.7 newtons. You can do the same thing for sine. This is opposite over hypotenuse, or the y component over the hypotenuse. And this gives me my y component, if I rearrange, f sine of theta, or 40 newtons times sine of 50 degrees. And this will give me 30.6 newtons. So in this problem, we're asked to find the magnitude and direction of the net force from adding the three forces in this figure. So anytime you add forces, you always want to do it component-wise. So this means we want to get the x component of our resultant force. And to do that, we will add up the x components of each individual force. And we'll do the same thing for the y component. Okay, so we'll start with filling out our x equation. The first force is going to have an x component that is adjacent, or let's go ahead and write the magnitude, 200 newtons times cosine, since it's adjacent, so cosine of 30 degrees. And then F2 will be 350 newtons, and the x component here is opposite of this angle. So opposite is always sine, so sine of 20 degrees. We'll pull out our x component. And then for F3, actually, by the way, this should be negative since it is pointing in the minus x direction. Likewise for F3, it is going to be negative since it's going to the left. So this is going to be 150 newtons. And if we want to get the x component that is adjacent here. So we'll do cosine of 45 degrees. Okay, and if we punch that in our calculator, we get minus 52.57 newtons. We can do the same thing for the y forces, y components of each force. And the great thing about this is once you know which trig function goes with the x components, we can just use the opposite trig function. So sine instead of cosine and cosine instead of sine with our corresponding magnitudes and angles. So cosine of 20 degrees instead of sine. And this is going to be plus since both F1 and F2 have positive y components. F3 has a negative y component since it is down. So we'll do 150 newtons. And our x component was cosine, so our y component is going to be sine. And if you need to double check any of these, all you have to do is make your right triangles and label which components are adjacent and opposite. So this is F1x, this is F1y, this is F3x, F3y, and F2x, and F2y. I'm sorry, should be on this side, F2y. Okay, so now we punch this in and we get 297.04 newtons. I'm leaving a few decimal places because I still need to find the magnitude and direction of my resultant force. Okay, so the way I always do this is I draw my right triangle using these components. So my x component of the resultant force is negative, so I'm going to draw it to the left. So FRX. And then my y component is positive. So I'll draw that, FRY. And the magnitude of my resultant force is what I get when I connect them or make the hypotenuse of this right triangle. So FR. And I'm going to look for this angle. Okay. So first I'm going to start with the magnitude. So the magnitude is always given by the Pythagorean theorem. Okay, so we take the legs of our triangle, square them and add them together, and then take the square root. So FRX squared plus FRY squared. Just to show you what that looks like, be minus 52.57 newtons squared plus 297.04 newtons all squared. And punching that in, we get a magnitude of 302 newtons. And now if we want to find the angle, we typically use inverse tangent. And I'm going to do, so it's opposite over adjacent, and so for me that is FRY over FRX. And since I know what my angle is going to be here, I'm just going to punch these in positive. So 297.04 newtons over 52.57 newtons. And this will give me 80 degrees. So that is this angle here on my right triangle. And you're often asked for the angle counterclockwise from the x-axis. So if I wanted to do that, well, this is my positive x-axis. I want to find this angle. I'm sorry, not that angle. This angle. And so I need to take 180 and subtract my angle theta. Okay, so if I do that, this is 180 degrees minus 80, or 100 degrees counterclockwise from positive x. In this problem, we have a horizontal force of 56 newtons and it is applied to a crate that is resting on a frictionless surface. And we're asked to find the mass of the crate if it accelerates at 8 meters per second squared after being applied with this force. So if we draw, that's what this looks like. It's a horizontal force, and it is 56 newtons. Okay, and there's no friction, so the only force that we have in our x direction is this applied horizontal force. And so we can just immediately go to Newton's second law, where we sum up the forces in the x direction and set it equal to the mass times the acceleration in the x direction. So I always like to start by summing up the forces, but here that's just the magnitude of this horizontal force. That is our only force in the x direction. And then I take this force, which represents my net force, and set it equal to the mass times acceleration. And then the third step, I'm going to solve for what I want. And so in this case, not acceleration, I want to find the mass. So I'll take my 56 newtons and I'll divide by the acceleration, which was given as 8 meters per second squared. So you have 56 newtons divided by 8 meters per second squared. And 56 divided by 8 is just 7. So our mass is 7 kilograms. This next problem, we have a horizontal force of 16 newtons that is applied to the left of a 7 kilogram box that is resting on a smooth surface. So I'm going to go ahead and draw a box and get a picture going. So we have a 16 Newton force, call this F1. It's applied to the left of the box, so it's going toward the right. This is a 7 kilogram box. And then we have another 30 Newton force, which is applied to the right side of the box. So we'll call this F2 equals 30 newtons. And we're asked to find the acceleration of the box. So the first thing you should always do with a force problem, especially when you have multiple forces acting, is to draw a free body diagram. So since this box is resting on a surface, we know there is a normal force. All of our objects that have mass are going to have a weight, and your weight is always straight down since it's the force of gravity. Our F1, our first horizontal force, is acting to the right. So I'll write this 16 newtons. And then I'm going to draw this force a little bit bigger since it is bigger in magnitude. And F2 is 30 newtons to the left. Okay, and now that I have that, I'm ready to start doing Newton's laws. So I'm going to sum up the forces in the x direction. Okay, my first step. So that I have a positive F1 to the right and a negative F2 to the left. Okay, this is my first step. Then I want to take this net force, what I got for the net force, F1 minus F2, and set it equal to the mass times acceleration. And the third step will be to solve for what I want. In this case, I want to know the acceleration of the box. So I need to divide both sides by m, and I get F1 minus F2 divided by the mass. And if I plug that in, I get 16 newtons minus 30 newtons over 7 kilograms. Or that 16 minus 30 is a minus 14 newtons over 7. So that is a minus 2 meters per second squared. And this minus sign, you should always ask yourself when you get a negative number if that makes sense. And in this case, the larger force in the x direction is pushing to the left, so it's going to overpower this 16 Newton force, and the box is going to accelerate in the minus x direction. So this is just acceleration to the left. So that's all that means. That's perfectly fine. Okay, our next problem. A constant horizontal force of 80 newtons is applied to a 10 kilogram box that is initially at rest. find how far the box has traveled after a time of 3 seconds. So I'm going to start by drawing a picture of my box. And I have a horizontal force of 80 newtons. So I'm just going to put Fx since it's horizontal. It's 80 newtons. And I'm given a few different numbers here, so I'm going to go ahead and write the things that I know. First, I know this force is 80 newtons. I have a mass of 10 kilograms, and I'm given that it is initially at rest. So if it's moving in the x direction, then v naught x is 0 meters per second. And I'm given a time of 3 seconds. Okay, so this might be useful in some equations later. The first thing I want to do is use Newton's laws to figure out how much acceleration this force is going to cause. So I'm going to sum up the forces in the x direction and set that equal to mass times acceleration. So in this case, my net force in the x direction, so sometimes you might write this as F net x, is just this horizontal force of 80 newtons. Okay. Then once we know the net force, we can set it equal to ma. So we have 80 newtons equals mass times acceleration. And we want to find the acceleration, so our third step is to solve for what we want. So we're going to take 80 newtons and divide by the mass, or 80 newtons over 10 kilograms. That's pretty easy. That's 8 meters per second squared. Okay. Now the problem said that this is a constant force, and since it's the only force acting, a constant force, so if this is constant, a constant force will produce a constant acceleration. And when our acceleration is constant, that means we get to use our kinematic equations. Okay, so if we look at what we're given, we have time. There's two kinematic equations that have time, and we're given, we're looking for how far, so we want to find delta x. So the kinematic equation we should use is delta x equals v naught x times time plus 1/2 ax t squared. Okay, this has everything we need plus what we're looking for. First off, I'm going to set the initial velocity equal to 0. And then we just have the distance, delta x, that it travels is 1/2 times our 8 meters per second squared we just found, times the 3 seconds that it was traveling squared. And if we punch that in, we get 36 meters. Okay, so it's really good to look at your forces and pay attention when you see things like constant forces, because that tells you a constant net force will produce a constant acceleration, and then that sort of gives you permission to use your kinematic equations. Okay, one more problem. This is kind of a classic boy in an elevator. So a 45 kilogram boy stands on a scale, and first we want to find the weight of the boy. Then, if the boy stands on the same scale in an elevator that is accelerating upward at 0.8 meters per second squared, how much will the scale say the boy weighs? Okay, so first, maybe I just draw my scale, my boy on it. Okay, and then if we draw a free body diagram, the boy's resting on the scale, so the scale is going to apply a normal force to keep the boy from going through the surface of the scale. And then the boy's weight is going to be down, as always. So for part A, we're asked to calculate the weight. So our formula for weight is mass times gravitational acceleration. Okay. So this will be 45 kilograms times 9.8 meters per second squared. And if we punch that in, we get 441 newtons. So your weight will always be in some unit of force. So weight is a force, so it will have units of newtons or maybe pounds, something like that. But mass will always have units of grams or kilograms. And so you don't want to mix up weight and mass. They differ by a factor of g. And so you always want to be careful, and that's really one of the things this problem points out is the difference in mass and weight. So now if we go to part B, we want to find out what the scale says the boy weighs when the elevator is accelerating upward. So I just put him in an elevator. It's going to be going up. So the acceleration in the y direction is positive, and it's equal to 0.8 meters per second squared. And so to do this, we need to use Newton's laws, okay, as with most force problems. So if we sum up the forces in the y direction, we will get the normal force and then a minus the weight, so a negative weight force since it's down. And we're going to set this equal to mass times acceleration in the y direction, okay? And we know what this is because it's given in the problem, okay? Now what we're looking for is the normal force. The normal force will tell you how much you appear to weigh. Okay, so if the boy wasn't moving, however much his weight is, that's how much the normal force is going to be because it's just going to cancel out the weight. But you know from being in an elevator, when you're pulled up, you kind of feel a little bit heavier. And so that normal force is going to change. And so we need to find out what that is, and that's going to correspond to how much the boy appears to weigh. So we need to move our weight to the other side. So I have my MAY, and then I'm going to add the weight to both sides to move it over. Now the mass is 45 kilograms. Our acceleration was given as 0.8 meters per second squared. And then we're going to add the weight that we found in part A, 441 newtons. And if we plug that in, we get a value of 477 newtons. Okay, so by the elevator accelerating upwards, the boy feels heavier, and it reads on the scale about 36 newtons heavier than it did when the elevator wasn't accelerating.